Let's continue our review of prerequisite knowledge for Calc 2 with some Calc 1 practice. We're going to evaluate some limits, some derivatives, and finally some integrals. These problems should all be reviewed, and I would again highly recommend that you practice solving the problem on your own first before we work through it together. All of these problems are very important to know as we begin Calculus 2. If you feel a little bit rusty on any of them, you want to make sure to practice with some further examples. Go back over the important rules for derivatives and integrals especially. Make sure that you're really comfortable with these concepts. They are foundational and essential to what we will be doing in Calculus 2. Let's start off with some limits. For these problems, it's really helpful to draw the graphs of the functions if we can. We just practiced drawing the graph of 1 over x. So let's just give a quick sketch here. 1 over x looks something like this. So we're first taking the limit as x approaches infinity of 1 over x. As x goes to infinity, 1 over x goes to 0. And another way of thinking about this is when we divide by larger and larger numbers, the result gets smaller and smaller. So this limit is 0. When x approaches 0, we actually have two different values. From the right, 1 over x goes to infinity, and from the left, it goes to negative infinity. So this limit does not exist. It doesn't actually have a value. How about example 3? Let's give a quick graph of the natural log function, which will help us to evaluate these limits. Here's what the graph of natural log looks like. It's important that you be able to graph this, to give just a quick sketch like this, from memory. We want to know what this graph looks like and have a working knowledge of how to picture it. All right, so as x approaches 0, natural log is plunging toward negative infinity. So the answer here is negative infinity. And as x goes toward infinity, natural log slowly keeps getting larger and larger. So natural log approaches positive infinity. How about e to the x? Well, once again, let's draw the picture of e to the x. This is another very important graph that we must have a good working knowledge of. E to the x looks something like this. Notice that it does not pass through the origin. It passes through this point here. This is the point 0, 1. So as x approaches 0, what does e to the x approach? Well, in this case, we can just literally plug in 0 into the function, and we have e to the 0, which is 1. Finally, let's think of example 6. Here, I wouldn't expect that we could draw the graph of e to the negative x squared. This would be a little bit trickier. But let's think of what happens as x approaches infinity for this function. The negative exponent, I think, makes it a bit trickier. So I think it's easier to write this as the limit, as x approaches infinity, of 1 divided by e raised to the x squared. Now, as x gets larger, e to the x also gets larger. So this denominator is getting bigger and bigger and bigger as x goes to infinity. We have 1 divided by larger and larger and larger numbers. The net result is 0. Now let's practice with some derivative problems. Derivatives are essential in order to do well in Calc 2. We need to know the derivative rules, especially the chain rule, the product rule. We need to be able to calculate derivatives quickly and reliably and be confident in our answers. So once again, I encourage you to attempt these problems on your own, try to do them first, and then we'll work through the solution together. This first problem is a chain rule problem. We have the derivative of e raised to a power. The derivative of e to a power is e to the power times the derivative of that power. The derivative of x squared is 2x. So there is the derivative of e to the x squared using the chain rule. For this next problem, we need to use the product rule. We have the square root of x times sine of x. And it might be a bit easier, if we can't remember the derivative of the square root of x, to write that as x to the 1/2. So we have the derivative of x to the 1/2 power times sine of x. We want to make sure to not just do derivative of x to the 1/2 times the derivative of sine. We must do the product rule to solve this problem. So we first start with the derivative of the first factor, x to the 1/2. That's 1/2 x to the negative 1/2. Then we multiply by the second function, no derivatives, just times the second function, plus the first function, square root of x, or x to the 1/2, times the derivative of the second, and now we can take the derivative of sine, which is cosine. This is using the product rule. Example 3. Let's rewrite as the derivative of 2 times x to the negative 1/2. That's what x to the square root of x in the denominator can turn into. Square root of x is x to the 1/2, and then because it's x to the 1/2 in the denominator, that becomes negative 1/2 in the numerator. This is the power rule. We bring down the power and we subtract 1 from the power. So we have 2 times the negative 1/2 times x to the negative 1/2 minus 1, and this gives us 2 over 2 is, those cancel, so we have minus x to the minus 1/2 minus 1, that would be minus 1/2 minus 2/2, that's negative 3/2. So negative x to the negative 3/2. Example 4, once again, uses the product rule. We want to take the derivative of x, which is 1, times the second function, no derivative, plus the first function, x, no derivative, times the derivative of e to the negative x. The derivative of e to the negative x is e to the negative x times the derivative of the exponent, negative 1. It's very important that we feel comfortable about the solution to that problem. Let's take a look at some other derivatives. Example 5. The derivative of the natural log of x is 1 over x. This is a rule that we just need to know. We'll see it all the time in Calc 2. It's a very important rule. The derivative of the natural log is 1 over x. And similarly, if we were to integrate 1 over x, that would give us the natural log. How about the derivative of 4 divided by x squared? This is going to use the power rule. At first, it looks like we might need to do the quotient rule since it looks like a fraction, but the quotient rule is more than we really need to do here. It's a little bit easier if we just rewrite as 4 times x to the negative 2. Now we can use the power rule. Bring down the power, negative 2 times 4 x to the negative 2 minus 1 is negative 3. So we have negative 8x to the negative 3. The derivative of arctangent is another rule that we just need to have memorized. It's 1 divided by 1 plus x squared. That's an important derivative rule that we should know by heart. Let's take a look at example 8. Here we could use the quotient rule if we wanted to, but it's a bit easier, I think, to simply rewrite. Instead of 1 divided by 1 minus x, we could write this as 1 minus x raised to the negative 1 power, and now we can use chain rule plus the power rule. So we start with the power rule. We're taking the derivative of something raised to a power. The power comes out front. So we have negative 1 times the something to the negative 1 minus 1 is negative 2. We still have the 1 minus x inside the parentheses. Now we need to use chain rule multiplied by the derivative of the inner function. The derivative of 1 is 0. The derivative of minus x is a minus 1. So we have to multiply by negative 1. That's the derivative of the inner function using the chain rule. We could simplify if we want. We have negative times negative, and this is 1 minus x to the negative 2. This simplifies to 1 divided by 1 minus x quantity squared. Finally, example 9. It looks like we might have to use the quotient rule because it looks like we have a fraction, but it's easier to think of this as negative 1/3 times the log. So let's write it as negative 1 over 3 times the natural log of 2 minus 3x. And the derivative of a constant times a function is just the constant times the derivative of the function. So we'll multiply by negative 1/3 times the derivative of the natural log of 2 minus 3x. The derivative of the natural log is 1 over whatever's inside. So 1 divided by 2 minus 3x. And now we need to use the chain rule and multiply by the derivative of this inner function. The derivative of 2 is 0. The derivative of the minus 3x is a negative 3. So we multiply by negative 3. And we can notice here that the negative 1/3 and the negative 3 cancel out. So we're left with 1 over 2 minus 3x. In the future, it's going to actually be more important to think of integrating this sort of an expression. If we integrate the fraction 1 divided by 2 minus 3x, we get this expression here. It's really reversing the chain rule, which we just did to take the derivative. So it's important to recognize that the integral of this fraction is this natural log expression. Let's wrap up our review of Calc 1 material by evaluating these integrals. These should all be integrals that we've seen how to do in Calc 1. We must be able to do these sort of simple integrals very reliably. So once again, please take the time to practice these. Try to work through the solution on your own. If any of them feel rusty, you definitely want to review them. Make sure that you're comfortable with the rules before we get into the Calc 2 content. So example 1, the integral of 5. It's tempting to write 0, but that's the derivative. The integral of 5, this is the function whose derivative is 5, is 5x. It's easier to think going backwards taking the derivative. The derivative of 5x is 5, so the integral of 5 is 5x. We want to remember the plus c since it is an indefinite integral. Now we have the integral of negative x. This is negative x to the 1. We increase the power by 1 and divide by the new power. So this becomes negative x to the 1 plus 1 is 2, divided by 2 plus c. Once again, go backwards by taking the derivative. Think of taking the derivative of negative x squared divided by 2. You have negative 2x over 2. Yes, indeed, it's minus x. All right, now we have the derivative, or the antiderivative, of 2x squared. The 2 is just a constant multiplied out front, so we just continue to multiply that constant. And now we focus on the integral of x squared. This is a power. The antiderivative of a power is to increase the power by 1 and divide by that new power. So x squared becomes x cubed. We increase the power by 1, divide by the new power, add on a plus c. Once again, it's very important to think of going back by taking the derivative. The derivative of x cubed is 3x squared. The 3's would cancel, and we would have 2x squared. That's where we started. We can always check any integral by taking the derivative of the answer, and it should be exactly what we started with. Problem 4, we want to rewrite the square root as being 3 times x to the 1/2, and we can once again apply the power rule. We increase the power by 1, x to the 1/2 plus 1. That would be 3/2. We divide by 3/2. Instead of dividing by 3/2, this is a little bit messy. I prefer to simply multiply by the reciprocal. So instead of dividing by 3/2, I usually skip over this step here, and I multiply by the reciprocal 2/3. So this would be 3x to the 2/3, to the 3/2, times the reciprocal of 3/2, 2/3. We could cancel the 3 if we wanted to, simplify a little bit, and we have 2x to the 3/2 plus c. Once again, if we take the derivative, we'll get back 3 times the square root of x, exactly what we started with. Example 5. We have the integral of 4 divided by x. We can take out the constant 4, so we have 4 times the integral of 1 over x. This is a very important integral that we'll see a lot in Calculus 2. The antiderivative of 1 over x is the natural log of the absolute value of x. So there's our answer for example 5. For example 6, it might be tempting to say that the answer is the natural log of the absolute value of x squared. But this is actually false. In order to solve this problem, we need to rewrite the fraction as x to a power. So 1 over x squared is the same as x to the negative 2, and now we can apply the power rule for antiderivatives. We increase the power by 1, x to the negative 2 plus 1. Negative 2 plus 1 is negative 1, so we divide by that new power, negative 1. The answer is, well, negative 1 here just makes everything negative, so we can write this as negative x to the negative 1. Or, I prefer to write it as negative 1 over x plus c. Notice that this does not use the natural log. It might be tempting to try to write natural log of x squared based on this sort of a rule here, but we only get a natural log when we have an x to the first in the denominator. Example 7 is kind of similar. We want to rewrite this to be 2x to the negative 1/2. Once again, we use the power rule for antiderivatives. Increase the power by 1, so 2x to the negative 1/2 plus 1 is a positive 1/2. And instead of dividing by 1/2, we can multiply by 2. So this becomes 4x to the 1/2 plus c. Once again, for all these problems, try taking the derivative to check the answer. If we take the derivative of 4x to the 1/2, we would get 2 divided by the square root of x. 2 more examples. The integral of sine is negative cosine of x. And the integral of cosine is positive sine of x. It's easy to confuse these, but once again, think of taking the derivative. The derivative of cosine is negative sine, So we want the negative here to counteract the negative from taking the derivative. Negative, negative, positive sign. The derivative of sine is cosine, so the antiderivative of cosine is sine.